Hey, it's Tony from Adafruit, and in this video we're going to look at the SSD1306 OLED display with MicroPython. And I did a video on this before with the ESP8266, but I wanted to do a new video because there's a new guide out that shows a really easy process for using these little or these little OLED displays, and hopefully shows kind of the process for how you can use modules with MicroPython kind of going forward. So we'll show kind of a new method for importing them and using them in your own code. So it's good to kind of revisit it and also just show here there's a good guide that shows how to wire these displays up and start using them. So we'll just kind of dive in and get started, and hopefully everything's working. I've got a new microphone set up, so the audio stuff, I think it's okay, but we'll see how it goes. I do notice the CPU usage is a little bit high, so might have to play more with that later. So if there's some stuttering, sorry for that. Try to bear with me. It usually improves when I go to the main shots. So let's go back to, or let's go to the desktop, the main shot here, and it looks like it's all right. I think the CPU usage is a little bit better. So, oh, interesting. I'm apparently only in one channel instead of stereo channels. So, well, I guess it's hey, we're running on the fly here. I'm not sure how to get Wirecast to mirror this stuff. Let's see. We'll try to do some quick debugging here if I've got some source settings. So the new thing is I've got this fancy little audio preamp. I'm afraid to change the settings right now, so it's I don't know, I'll have to mess more with this later. So for now, hopefully this video isn't completely terrible. Hey, I'm in the left channel, so we'll see what we can do maybe in post to fix some of the stereo stuff. So anyways, this is the guide that I'm going to talk about. This is the SSD1306 OLED display MicroPython guide that I'm showing in the web browser here. And I'll put a link when this goes up on YouTube so you can go and check it out yourself here. And this basically just walks through how to connect these displays to your MicroPython board and then how to start using them in MicroPython. And like I said, I did a video on this before, but I want to show an easier process in this video on how to do it. Now in the upper right hand corner I have a couple things up here. The top thing here, this is the OLED feather wing. So this has an SSD1306 display, 128 pixels across by 32 pixels down. So nice small display. Great thing is it's the feather form factor, so it just slots right into a feather board. Like this one right here is the SAMD21 basic proto feather board that's running MicroPython. So if you saw last week, we had a guide and a tutorial and video and all kinds of stuff on a version of MicroPython that runs on these SAMD21 based boards. So definitely check that out. I'll put a link in the description so you can see that. And then over here, this is the ESP8266 feather, and then this is connected to an SSD1306, an SSD1306 display. This one's a little bit larger. This is 128 pixels across by 64 pixels down, and it's connected using a SPI interface. So it's a different interface compared to the feather wing. This uses an I2C interface. So we'll talk maybe a little bit more about some of those differences, but some of the displays use one interface, some of the displays use another interface, so you'll need to use the right interface. And this guide kind of shows you how to use both of these. So in the guide, I focus on both of these chips, the SAMD21 MicroPython port and the ESP8266 MicroPython port, but this should work on other MicroPython boards. So things like the Pi board, the YPi, you might need to slightly change how you initialize I2C or SPI, and I mentioned that in the guide just because each port can have a little bit of a difference in like how the pins are named, and even sometimes how you initialize some of these hardware buses. But the overall usage should be the same across these boards. So we'll kind of dive in, and basically the guide, it just starts kind of giving an explanation. And if you're not familiar with MicroPython, definitely check out in this guide, you know, like what is MicroPython guide, how to load it onto your board, that type of stuff to get started. And then this link here, all of the MicroPython guides in the learning system, this is really handy. This takes you to the category where you can see there's about 12 or 13 guides so far that go into more detail on all the different parts of MicroPython. So let's dive into the hardware here for this. And to follow this, obviously you're going to need what I have here. So a MicroPython board, and in this guide I'm really looking at the ESP8266 and the Feather M0 boards, but anything should work just with a few modifications to the code that I'll kind of call out. And if you are using the Feather, like I said, the Featherwing OLED is perfect because it just slots right in and it's easy to use. But you can use an external breakout here. It has to be an SSD1306 display, so make sure you've got one of those displays. And that it can connect to your MicroPython board with the appropriate interface. Like the SAMD21 MicroPython, right now we don't have the SPI interface enabled completely, so you can't use like this display with it, for example, but you can use an I2C one, and that's fine. The ESP8266, it supports both SPI and I2C, so you should be okay with any display, but it does have like a software SPI or software I2C implementation, maybe even a software SPI implementation. I can't remember exactly how they did it, but it could be a little bit slower in some cases because of that. But anyways, so you need basically just those components, the display and your board, and you're pretty much good to go. And then I just kind of show how to wire this up. So if you're using the Featherwing, it's as easy as just plug it in. So I'll do that actually right now. I'll just slot it right in, and there it goes. So that's done. That's as easy as it gets. You do have to solder the headers onto here, obviously, for some of these boards when you get them, so you will need to do a little bit of assembly. And like I mentioned in the guide, it's maybe, I probably should have bolded this, but follow all of the guides for your products. So when you get this little Feather OLED, follow its guide. So it'll tell you how to solder the headers on, how to test it out in like Arduino, for example. Go through all those guides first, just to make sure that your product and things are working and you understand kind of how to connect it before you dive into using it with MicroPython and other stuff. And then I just kind of show, okay, if you're manually wiring up to I2C, it's pretty simple. Just the clock and the data lines need to be connected, and then a power and a ground line. And you can power it with like 3.3 volts, for example, but most of our breakouts have regulators on them, so you can power like 5 volts in if you need it for that. But check the product description, check the guide for each of the boards that you're using. And then if you're using the SPI interface, this shows the wiring for that. So a few more wires that you need in that case. There's still a clock wire. There's also a data output wire, this orange one here. And then you need a DC wire. This tells it if the board should receive a data or a command byte. And then there's a reset line and a chip select line. So these are kind of standard SPI interfaces, at least the chip select. Reset just resets the display for this. So super easy to wire this up. Just connect it pretty much to all the SPI pins. And then you need some GPIO pins for the reset, the chip select, and the DC line. And I mentioned you can use any GPIO pins. In this example, I'm showing the ESP8266 and some of the GPIO lines here, but really, use what works for you on your board. Okay, so and that's exactly what I've wired up here. So let's get into the software for it. So it's pretty simple and straightforward. And again, this is kind of showing a preview maybe of how hopefully using modules in MicroPython will work in the future. Modules for things that Adafruit produces specifically. So like our Featherwings, like this Featherwing OLED, or for example, in the near future, you might see this. This is the PCA9685 PWM driver Featherwing. Again, it's a Featherwing, just slots right onto these boards. And hopefully we'll be able to start distributing some of these as modules that you can just download a file, copy to your MicroPython board, import, and start using the code directly. So you don't need to like recompile a MicroPython firmware, which I've shown in the past, like to freeze in a module or things like that. There's actually some new support, and so I do mention here you need to be running the very latest version of MicroPython for your board. So for the ESP8266, you need to run version 1.8.5 or higher, and this only came out like a week ago as of the recording of this video. So if you've got an old board lying around with MicroPython, go and update it, because you do need this latest version. In that version, they added support for importing these .mpy module files, and so you really have to have that support for this. For SAMD21 MicroPython, you also want to grab the latest version, even though it just came out like Monday this week. We've got a new version actually that just came out a few days ago. So you want this. This enables a frame buffer module that's necessary for this. So follow the guide. Make sure to get at least these versions. If you're watching this video later, there are probably later versions that I'm assuming are going to be okay to use with this. Okay, so that's what you need. So make sure you're running the latest MicroPython, and both of these boards I've already preloaded with the latest versions of MicroPython for them. And again, I have the SAMD21 board right here, and then this is the ESP8266 board right here. And then the next thing, so here's where it gets fun. So now we need to download this SSD1306.mpy file. So this is the code that can talk to the OLED display and give you a simple interface in MicroPython. So you can say, set this pixel, or draw this character of text, or this line of text. And so you can go to it. It's actually on GitHub. So there's this MicroPython-Adafruit-SSD1306 repository. So this is where the source code lives. It's open source. It's based on the code that's in the MicroPython upstream repository. We just broke it out into its own repository because it needed a few fixes to work with our SAMD21 board. And in general, it's kind of nice in that we can have our own list of GitHub issues and like releases with files on here. So we kind of made it separate from the source repository for now. But the code it's just straight MicroPython code that's using I2C or SPI to talk to the display. And so the nice thing is it gives you a simple interface. So you've just got some functions here like filling the screen or setting a pixel. And we'll come back and look at these. Now you could just copy this .py file onto your board and import it and use it. I've shown in previous videos how to do that. But the big problem is that uses a lot of memory because it needs to load this entire file into memory. And this is not a small file. Let's see if we can see the size. Yeah, it's about 5 kilobytes of text. So that's a lot of data. That eats up a lot of RAM potentially. So you don't want to do that. Now the cool thing is if you go to the Release tab, and I mentioned this in the guide, we have this .mpy file here, and I've done a video on this before, but basically these .mpy files are pre-processed MicroPython source files where it takes that raw text source code and converts it into a smaller version of it, kind of a bytecode format that MicroPython interprets internally. So it's a smaller file, and even though the file size is about 4K, you know, it's a little bit smaller than the previous file, it uses much less RAM when you import this. It still has to use some RAM, but it's a lot better than just loading the raw Python source code. So it looks like a good compromise in that, you know, if you're using lots of different peripherals, you'll download these .mpy module files, copy them onto your board, and start using them. You could reduce the memory usage even more by making this an internally frozen module, and I talked about this in the last video I want to say that I did on the SAMD21 firmware, where basically you can build a custom MicroPython firmware that includes this module inside of it, but there are trade-offs to that because that increases your firmware size. So try the .mpy files. This looks like a good way to use these. So to make this work, I just need to copy this file, so I'm going to grab the link to this, and then on my machine here, I'll just download the file with wget. You know, you can do whatever. You can just download this through your browser if you want. Then once I have the file, I need to copy it onto a board. So let's start with the SAMD21 board first. So I'll plug this guy in, just connect it. There we go. And then let me make sure that this doesn't move around too much here. I have to probably have something that holds it around. Well, that's close enough. There we go. We'll zoom in on that. How about, so we go in. There we go. That's perfect. Okay, so I've downloaded the file. Now I need to get it onto my board. And remember, the cool thing with the SAMD21 board is it shows up as a USB mass storage device. So if I open up Finder, you can see right here, here's this MicroPython drive, and then I can copy things onto here. So I can like copy that .mpy file that I got. So let me grab it from the directory that I have it in here, and I'll copy it. And then we'll go back to the MicroPython drive. And okay, so I'm just going to paste this in. And so that's going to copy the file onto the board's internal file system. And then right now with the SAMD21 port, make sure to eject the drive. And then once it's done ejecting, I'm going to reset the board. I'm just going to press the reset button. And this is good. This is just to ensure that the file system picks up this new file, because right now there are some caching issues that are actually fixed in probably the latest build that we'll get out soon. But anyways, okay, so I reset the board, and then just to double check, I'm going to connect to the serial repl on that board. So let's connect to dev tty, /dev/tty.usb modem, 115200 baud, and I've got the Python prompt, so everything's working. And if I really want to check that file is there, I can import the OS module and call listdir, and then you see, there it is, the SSD1306.mpy file. So cool, so it's on my board. You could also use Ampy or any of the tools for me, so or any of the tools that you've used before to upload code to the board. So, you know, USB mass storage is fine, Ampy is fine, anyway works. You know, just get the file onto the board, basically. Okay, so at this point, you can actually import this module. So just run import SSD1306, and there you go. It's loaded just like its Python source code. So we'll come back and we'll use this module in a second. So I'm going to go back to the guide, and we'll dive into the hardware, the usage of this. Okay, so for this Feather Wing, it uses I2C, And so I need to follow the I2C initialization part of the guide. There's also a SPI initialization part of the guide a little bit further, and we'll come back to that because that's how I have the ESP8266 hooked up. Now this shows for the SAMD21 MicroPython port how to initialize I2C. Again, check for your board because each board is a little bit different. The pin names are different sometimes, and like for the SAMD21 board, you have to initialize I2C or use a context manager, and I'll show you a little bit more later about this. But let's just run this code here exactly. So this is kind of the default if you're using the OLED feather wing on the SAMD21 board. So I need to import the machine module and then create an I2C interface that's just inside of that machine module. There's a class, and I need to pass it the pin that's the clock, and so that's the SCL, the I2C clock line, and then the pin that's the data line, the SDA line. So for the feather wings and the feather boards, this is the default that you want to use for SAMD21. Then I need to call I2C init just because I'm in this REPL and I need to tell it to initialize that I2C bus. And then just to double check, I can run I2C.scan, and I want to make sure I see this 60 value back because that means that it sees a device with address 60 on the I2C bus. So it can definitely tell that that OLED display is talking to the board. So it's a good little check just to make sure that, you know, if you didn't see that 60 device, then maybe the soldering is bad on the headers or something's wrong with the connection. Maybe it's not powered up. So double check that. You do want to check that you can actually see the device before you use it. Okay, at that point then, we're pretty close to being done. Now I just need to create an instance of this OLED object, and so that's why I imported that SSD1306 class. And so to create this, it's pretty easy. We'll just create an OLED variable and we'll assign it to the SSD1306 module. Inside of it, it has an SSD1306 I2C class. That's what I want to use. Now it takes two required parameters up front. There's the width of the display in pixels. So for the feather wing, it's 128 pixels wide, and then the height of the display in pixels. So this is 32 pixels tall. And then the I2C bus that I created ahead of time. So that I2C variable, I need to pass that in there. So I do that, and then at this point I'm ready to start using the display. So I go down in the guide and I talk through the basic drawing commands that you have right now, and it's really limited. You can really just set pixels, draw text, and fill and clear the screen. So, you know, there's not like line drawing or circle drawing or things like that yet, but in the future, keep an eye on things. I'm sure that these libraries will change over time, and we'll see more things like that. A nice little basic drawing library. But it's really easy. So the fill command, this takes a color, and remember these are monochrome displays, black and white, so the colors are either 0 for black or 1 for white. So if I fill with the color 1, that's going to fill the screen white. Now you don't see anything because the way these displays work, you change all the pixel data in memory, and then to actually update the display, you have to call this show function. So you do that, and then you see, hey, look, it turns on, it's all white. And then I can also clear it back to black by filling it with 0, and then again I have to call the show function to do that. So that's pretty easy. You can just like blank out the whole screen with that. There's also a pixel function. So this takes the X and the Y position of the pixels, so like 0, 0 will be the origin or the upper left-hand corner, and then the color, so I want to use color 1 for this pixel. And then let's just show like maybe the bottom opposite corners, like 127, 31, because remember the positions go from 0 to the maximum width. So 0 to 127 or 0 to 31 on the height. And then we'll set that pixel, and then let's do a show. And now you can see, so there's a little dot up there and a little dot down here. So here's the 0, 0 position up here, and then here's the 127, 31 position. So it's 127 pixels across, actually 128, because that pixel right here is at position 0. So at position 127, and then at Y position, or your height position 31, is kind of the far right corner down there. So that's pretty easy, and I can go and clear the screen again. And then the last function that's super useful, and really what I think a lot of people might want to use this for, is the text function. So this uses a font that's built in. You can't change it right now unless you get in and actually modify the firmware, but it's a simple little 8x8 pixel font that's perfect for drawing on these little OLED displays. And this is really nice. So you can actually just draw a line of text. So you can send in some text like hello. You give it the starting X and Y position. So let's just say 0, 0. And this is going to be the top left corner of that string of text. You'll see in a second when I show the text on the screen. So we'll say position 0, 0. It can take an optional color, but by default it's just going to use the color white. So we'll stick with that. And then if I do show, you can see, hey, check this out. So it says hello. And so if I zoom in a little bit, Hopefully we'll focus here in a second. There we go, we're sort of focused. So you can see hello, and it's basically showing, position 0, 0, it's the upper left-hand corner for that. I could put a line of text below that if I want, so we'll say like world, and then let's offset this a little bit. Let's say position 10 on the x-axis, and then position 10 on the y-axis. So this will move it down 10 pixels and move it to the right 10 pixels. And so maybe imagine where you think this will look, and then there you go. You see, it's offset a little bit and off to the right there. So super easy, super simple. This is perfect though. You can fit 3 lines of text because the text is 8 pixels tall. So you can get 3 lines of text comfortably on this little 32 pixel display. And this is excellent. So you could show like sensor readings, maybe the current state of your device, stuff like that. Really super simple and easy. And again, like, this is Python. So if I wanted, I could say, how about foo, and then I can use like a string formatter if I wanted to throw in, like a sensor value or something, like about 100 or something like that. So it's going to put the value inside of there. And then let's put this maybe at position 0, but 20 pixels down. And so now if I show this, now we see foo 100, for example, down there. So that's, how you might print out like a sensor value or some reading that you had. You can use like the string formatters and just standard Python syntax for this stuff. So that's really cool and really powerful and super easy, just a few lines of text, and we're just doing this all interactively, which is the cool thing about MicroPython. We're in this serial REPL running the code and making it work on this display. Okay, so that's cool. So I'm going to exit out of here, and let's try the other display. So let me zoom back out, and let's try the ESP board over here. So I'm going to disconnect the SAMD21 board, and let's try the ESP8266 over here. So again, I have this wired up in a slightly different way. So this is using the SPI interface, and this is a slightly different board. So this board has a larger display. So it's 64 pixels tall instead of 32 pixels tall. And I'll show you how to deal with this board. So first of all, though, again, remember from the guide, you have to copy that .mpy file, that SSD1306 MPY file onto your board. Now for the ESP8266, it doesn't support the USB mass storage, so it doesn't show up as a drive on your computer, unfortunately. But remember, you can use something like AMPI, and go back to the What is MicroPython guide and the How to Load Files and Run Code guide. That's where I talk about this tool called AMPI that lets you load files onto a MicroPython board. So a real simple little tool that just uses the serial connection. So we'll use that with the ESP8266. So to use AMPI, I have it installed already, and again, I'll put a link to the guide, so if you aren't familiar with it, you can learn how to use it. But basically, you want to point it at your board serial port. And I'm going to simplify things by just setting this AMPI port environment variable to the serial port of my ESP8266 board. So it's the TTY Scilabs USB to UART board here. So this way I don't have to constantly specify this port parameter whenever I make AMPI command calls. So I'm just going to run AMPI ls. This lists the files that are on the ESP8266 board. There's only the boot.py, so I want to put that SSD1306.mpy file. Remember, this is the exact same file that I downloaded from GitHub. You can use it on both of these boards, the SAMD21 and the ESP8266. And I want to put this file onto the file system, so that's the command that I want to run. So I do that, and that's going to send the file over to the board and save it on the file system. So now when I run AMPI ls, I can see I've got the SSD1306.mpy file there. So just like I did with the SAMD21 board, instead of using the USB mass storage, which you don't have on the ESP, I'm just using the AMPI tool here. So let's connect to the REPL on this board. Let's see, TTY Scilabs 115200 UART, or baud rate. And okay, so now we're just going to do really similar code to initialize this. So again, we're not using I2C. This is hooked up using the SPI interface. So I need to scroll down and just see the initialization. Now this is showing for the ESP8266 how to initialize SPI. Again, check your board because each board can be slightly different. There's this parameter here that kind of defines which SPI interface. So depending on how you have it wired up to your board, you might need to change this to a different value, like a 0 or a 1 or something like that. But let's just get going. And again, remember, I'm running the 1.8.5 version of the MicroPython firmware. If you're curious, press Control B. The letter B is in boy, and that will do a soft reset when you're in the REPL. And so that's kind of nice in that it'll print out, here's the version of MicroPython. So this is ESP8266 1.8.5 on here. And okay, let's import the machine module, and then I need to create a SPI interface. And so I do that, and again, for the ESP you want to pass in the value 1 because that's just what it expects for its SPI interface. And then you do need to pass in the baud rate and the polarity and the phase. This depends on the device that you're talking to. So for these SSD1306 displays, you can use a baud rate of 8 megahertz. So 8 million is a value that I'll pass in here. And then the polarity, and you could use a slower baud rate if you wanted. And in fact, sometimes the hardware doesn't actually support that exact baud rate, so you'd get a slower version in some cases, which usually doesn't matter. Now the polarity and the phase have to be 0 because these are values that differ based on each SPI device and how it expects the communication to work. So you kind of have to look these up or look at, in these guides, for example, like I'm showing, here's how you initialize it. So just be careful and be aware that this is a mode 0 device for SPI, so you need the polarity and the phase to be 0. Okay, so I do that. And then the next thing that I want to do is create an instance of this OLED class. And it's similar to what we did with I2C, but there is one big difference. So first I want to import that SSD1306 module. And again, look, it just worked. It's that .mpy file. If you get an error at this point, you're probably not running the 1.8.5 version of the firmware because only that 1.8.5 version and higher support the imports of MPY modules. Okay, now I need to create this OLED object, and I'm going to create this from the SSD1306 module. And inside there is an SSD1306 underscore SPI. So instead of I2C, we want to use the SPI one. And at this point, now the parameters change a little bit. So again, it takes in the width and the height of the display. So it's 128 pixels by 64 pixels actually tall, because this display is slightly different here. And then it needs to take in an instance of this SPI interface, so what I created above right here. And then there are some GPIO pins you have to pass in, because remember, there are those extra wires. There's the DC wire, there's the chip select, and the reset wire. And each of those are connected to GPIO pins, so I need to tell this class how those are connected. And so in the guide here, I just explain you want to use, basically the order that you should pass these in is the DC, the reset, and then the CS lines. And so the way I have mine wired up, I'm just going to use pin 15, 0, and 16 like I show in the guide right here. So I'll paste this in, and then there we go. Okay, so at this point the class is initialized, and I can use it just like the I2C class. So I can say fill with the color 1, and then show, and hey, look at that, it's all filled and ready to go. Or I can go and clear it again, so fill with the color 0, and then show it, and it's all cleared off. And then text, of course, that's going to work the same way. So we'll say hello, 0, 0. Let's put a line below that, world, 0, 10, like that. And then we'll show our text, and check that out, hello world. So super simple, super easy. Oh, there is one other function that I didn't show. There's an OLED.invert function. So, invert, it takes in a true-false value. So if I want to invert it, I can pass in true, and then see, it just inverts the display. And actually, let me zoom in a little bit so you can kind of see here. So that's kind of cool. Gives you, a little bit more of a different look to your display. And then you can turn off the invert with invert false. And notice you don't have to call show after doing this, because this is actually changing some hardware registers directly that just control how the display looks. So you won't see, like, it doesn't actually change the buffer and memory, which requires calling that show function. But that's really all there is to drawing text on here and drawing pixels also. So remember, you can still use the pixel function here. But it's that straightforward and simple, so it's really not too hard. Let me zoom back out so we can kind of see everything here. It's really just copying that .mpy file onto your board. That's the Python module, and then importing it and using it. So it's, straightforward and simple. It's, maybe easier in some ways than like Arduino, where you might have to install a library and figure out where to copy that. Although they do have the library manager now, which makes things a lot easier. And someday there's a lot of talk of maybe some, library management stuff for MicroPython. So who knows? We'll see in the future what happens. But for now, this MPY file install seems to be a pretty easy, good way to make this work. So that's cool. The last thing I wanted to show is, let's go back to the, actually let me close out this REPL window first. Let's go back to the SAMD21 board. So I'm going to plug this one back in, and this has the Featherwing OLED connected to it right now. And I'll show a fun little demo that I made just a little while ago, right before doing this stream. So let me zoom in. So I wanted to show maybe a more complex example of using this OLED display. And so I made a little message scroller, and I'll show you how it works first. So let's see, so I've got my board plugged in. And then let me change my ampy port variable. I'm going to use ampy to run a script. So I need to change the port for my device because this device shows up as a different name versus the ESP board. So I want to change this to this USB modem device. And now let's do ampy run -n because the script I'm going to run has an infinite loop, so it runs forever. And that -n means don't wait for any output. Just start running the script and finish. And then scroller.py is what I want to do. And so this is cool. So check this out. You can see this little message is scrolling across in a sine wave. And if you remember, I've done a bunch of streams on like old school demo scene effects. I don't know, it's something I grew up with. It's fun to revisit. So this is an old effect that you would see in demos of just scrolling a message across the screen in a sine wave. So it's kind of bouncing up and down. And so you can see it's, you know, hello world. This is a fun scroller. And so, okay, so let's look at the code for this. I'll actually show you how I implemented this. And I'll put a link to this. I put it up on a gist or a gist or whatever on GitHub. So I'll put a link to this in the video description below so you can kind of see the code for this. But I thought it'd be fun to, you know, make a more real example of how to use this display. You know, something that's more than just drawing a pixel. Okay, so the way this works, you know, I can modify this message. So, and just to make sure it works, we'll say MicroPython rocks. We'll say that is the message. And now if I run this, then we should see, you know, there it is, MicroPython rocks. So that's kind of cool. So this is the variable that controls that message. And then I have some other configuration up here where like you have to configure the size of your display and the font width and height. And even though those are fixed to 8x8 pixels, who knows, in the future this might change. And so it's nice to write my code so that I can adjust this later. Now the amplitude and frequency, these adjust the sine wave. Frequency is probably what you want to change. So frequency is how many times the sine wave makes a complete up and down cycle within the entire length of the display. So right now it's doing 2 cycles, and you can see as you watch the text, you know, it goes up and down a couple times because those are the, you know, the up and down cycle of that sine wave. So I can increase this, like let's go to like 5. So this is really going to be rocking all over the place. Like this is going to do 5 complete cycles. So this thing's going to move a lot. Yeah, see, check that out. It's kind of a neat effect. A little hard to read though, so this might not be the most legible thing. But you can bump it down too. I can say like 0.5. So it's only going to do like half a cycle when it's going across the screen here. So you can see it's kind of a, you know, a little bit slower effect, almost like a smile there. That's kind of cool. So, you know, MicroPython rocks. That's kind of cool. I could say, you know, like 1 cycle. So you just see like 1 complete sine wave as it goes across. So we'll do that. And then you can see. So that's, you know, that's pretty readable. That's kind of a neat effect. It gets the idea across for that. So that's kind of cool. I just wanted to make these configurable and easy to change. Now I'll show how this works. I have a main function right here that takes in an I2C object. The reason I do that is because way down at the bottom, this is actually the first thing that runs after it defines this main function. So I'm using this context manager syntax to create the I2C bus. So if you go back, this is for the MicroPython SAMD21 port specifically. And if you go to the guide for that port, I talk about what this context manager is. It just makes sure that you don't have to call that init and deinit function. It will do that automatically for you. And then because these context managers can be a little bit annoying because you have to have a whole indented block of code, I made this main function, and then I just call that main function inside this context manager, and I pass it in the I2C interface that was created right here with this line. So it just simplifies my code a little bit, and it's an easy way to use these context managers without getting really messy code. You know, I'm just putting my code into this function that I call. Okay, so I call this function, and then it's got some global state, so it's going to create that OLED display at the top here, just based on the width and the height of the display. And then I'm going to use a variable to keep track of what is the current X position of my scrolling message. So you can see as it scrolls across the screen, there's this position variable, and so, you know, it's moving kind of with my finger. Wherever you see that M, that's the first character, that's the position variable. And so the way that this script works is it just constantly scrolls that position variable across the screen, and when it gets off the screen far enough that it knows the message isn't printed anymore, it just moves position back to the far right side of the screen and then scrolls it back across the screen. So just going in a loop over and over so that it knows where to start drawing that message. And then I need to know like how long is my message in pixels, and so I compute that based on the number of characters in my message and the font width, so that I know once I've scrolled off the screen the number of pixels that my message consumes, I can go back to the far right side of the screen. Now the next thing I do is I actually make a lookup table to speed things up, because as I'm drawing all these pixels, like for each character, I need to figure out where, based on a sine wave, the Y position should be. Because remember, the sine wave just goes up and down all the time. Like, it's just a cycle. It's a signal that repeats over and over. And so it's just up and down, up and down. And I could compute that value inside of my main loop, but then I'm going to be calling a bunch of math functions and doing a bunch of things where the performance might not be that great. So, I only have 128 positions across this OLED display, and actually a few more positions, because if a character is slightly off the left side of the screen, I still need to draw it so that if you only see like half of the M character, for example, so there's a few extra pixels that I consider, and that's why actually the length of this lookup table is my display width plus my font width, so that I can fit the entire display plus up to an extra character on the left side here. And so I'm going to go through and then compute the Y position for each of these X positions in my lookup table. And I do that just based on a sine wave formula right here. So I'm just taking the frequency, and then this is a standard sine wave kind of formula. You just 2 pi times frequency will let you adjust like how many times the sine wave repeats in a given period of time. Now the time variable I'm passing in, I'm actually computing as a value within the range 0 to 1, and that's based on which pixel I'm looking at across here. So, the very first pixel will have a value of 0, the very last pixel will have a value of 1. And so that way then, when it goes into this sine wave formula, it's going to use that frequency so it knows how many times to repeat. And that's why it's as easy as just changing this variable to say, okay, I want to repeat 3 times now. And then, it's going to pass in a different frequency here. And then because this time is scaled between 0 to 1, it's going to repeat that number of times as it goes across the screen right there. Now the amplitude, this is just controlling, how far up and down it moves. And so I'm just computing it based on the height of my display minus my font height, because I don't want, when it gets all the way to the bottom, it still needs to draw the font. So, I want to offset a little bit so that I'm only looking at, basically from the line 0 at the top all the way down to the size of my display minus 1 character of font, so that it'll fit the entire font on there. But you could change this amplitude if you want. I could like fix this to a value of like, 3 or 4 or something like that if I wanted. I don't know, just for fun. Let's adjust this to a value of 20. So this is only going to go 20 pixels up and down. So we should see it like just move. It's going to do the same number of iterations, although actually I adjusted the frequency here, so let's keep the frequency at 3. But let's see what this does when I run this. So now we see, okay, so now you can see, so it's only taking about 20 pixels. So it's, let's adjust the amplitude even less. Let's make it, how about 5 pixels? Let's see what this looks like. So we should see less pixels here. So there you go. That's actually kind of cool. So you can see it's only moving up and down 5 pixels in this case, and so it's kind of offset up near the top of the screen. But that's kind of cool. That gives it a neat effect. And so actually, this might be, if I want to really crank up the frequency, let's say 10 times. But let's do an amplitude. Let's keep that 5. Let's see what that looks like. So we should get some really funky kind of jittery text here. Uh-oh, I think something went wrong. I might have just broken something here when I did this. So let's put that back to 3 and save this file. So let's see. Oh, could not enter raw REPL. Well, let's try it again. Let's see if this works. Okay, there we go. I don't know what that was. Sometimes when Ampy tries to connect, maybe it got some kind of extraneous output that it didn't expect there. So, try your command again. Okay, let's try this again. Let's do a frequency of 10, and let's run this script again. There we go. So there you go. Wow, this is like really frenetic kind of psycho text in that case. But that's kind of cool. So, again, you can play with these values. You can tweak these things, adjust them. That's kind of the fun of this, is just learning and seeing how things change when you change some of these variables like this. And if you're writing code, if you're writing a demo like this, think about like what are the knobs that you want to be able to tweak as you're writing the code. Like I could have just fixed my amplitude right here to be my display height minus my font height. But, there's no fun in that. Like I want to come in and play with this later. So I made it a variable that I could change like this. Now you do see I do amplitude divided by 2, and then I do plus amplitude divided by 2. This is because a sine wave will generate values that go from positive amplitude to negative amplitude. But I don't want negative values because the pixels on my screen, the Y pixels, only go from positive values, from 0 to up to 32. And so that's what I'm doing. My sine wave function is going to output a value that goes from like positive to negative values. And then I'm going to offset it by my amplitude because I want to push it back into only positive values. So I'll never get a negative value. And then I have to do amplitude divided by 2 because by default the sine wave, the amplitude for the positive and negative side is your entire amplitude value. But in this case, for the positive and negative side, I want those to add up to the total amplitude of my signal and not just like, 1/2 of it basically. So that's kind of why I cut it in half, but play around, try, see what happens if you set a higher value for this. Okay, but so again, I pre-compute this all into an array that's my lookup table, so that in this table, for every X pixel position, it's telling me here is the computed Y position to start drawing that character. And so that'll save me some time later in that I don't have to do this math function in my main loop further below. I'll just look up in that function ahead of time. And it's only like 140 values, so that's not that many values. There's definitely that much memory on this board, so it's fine to store that in memory. If you had like a 1080p display or something, which that would be a hell of an OLED display to have. If you had that kind of a display, you might not have enough memory to store a lookup table like this. So again, little optimizations that sometimes are appropriate, sometimes aren't. Okay, my main loop, this is pretty simple. It's just an infinite loop. I clear the screen. I move my position one position to the left, so that's why it's scrolling across the screen like that. And then I check to see if I've scrolled off the screen so much that my message is not visible anymore. Basically, if I've gone to negative message length X position, then just reset my position all the way to the far right, basically my display width. So that's how the message will scroll across. And you can see it's still scrolling, it finished, and then it just jumped over to the right side there. And so that's what's happening here in this little check. And then I just go through each character, and I try to be smart. So I want to only process and try to display characters that I know are visible. So I go through and I go through each of the characters in the message. I grab the character. You might wonder why I'm not using the enumerate function. We just realized in the SAMD21 firmware we've got to flip on the enumerate functions. It's not supported. Next release we'll get it. But it's easy enough to do enumerate yourself like this. So I grab the current character that I'm looking at. So this just loops through each of the characters in this message. So it'll start with the M, then the I, C. Each of those individually goes through. Grabs the character, then it computes what's the X position of the character based on my position of my text string plus the number of characters that I've seen so far times the width of each character, and that's that configuration value. So I'm just looking at, okay, where is this character going to be displayed? Like, where is the starting position of this character? And then I check and see, is that within the range of negative font width, which is basically one character off the left side of the screen, up to the display width. So as long as my character is starting somewhere within that range, then I'm actually going to draw it. If it's not within that range, like if it's way off to the left side here and not visible, I'm not going to try to draw it, which makes sense because I don't want to waste that time trying to draw things that aren't visible. This string could be like kilobytes of text long, and that would take a lot of time to go through and try and draw each of those characters. So again, I try to be smart and do the right thing here. My cat is messing with the box over there, so you might hear some fun stuff. Okay, so if I do see that it is visible, then I'm going to just call this OLED.text function. I'm going to draw the character, draw it at the X position that I computed ahead of time right here, and then this is where I do that lookup. So I look up in my my table that I computed ahead of time based on my character X position plus the font width. I do this because, remember, I'm looking at X positions from negative font width all the way up to display width, but arrays in Python, you can't index with a negative value. At least I don't think you can. I haven't tried that. I can't imagine that would work. But so I have to offset these to say, okay, don't use negative indexes into this array. Add font width in here. So if I'm at the negative font width position, that's actually going to be position 0 in my lookup table for that. So that's kind of why I do that adjustment there. And that's it. So it just draws each character and then shows the OLED display. I don't even actually have a delay in here, so this is just running as fast as it can right now. And it runs reasonably fast. I think this is fast enough, for these displays to work. You could slow it down if you wanted. If I wanted to put like a time.sleep inside of here. So let's put in like time.sleep 0.01, maybe like a millisecond of delay. So something kind of small. And then let's maybe change the frequency. So we're back down to 2. And yeah, we'll go back to the big amplitude again. And so now if I run this, we should hopefully see, uh-oh, I might have gotten the same little error there. I'll have to look at this later. So I'm going to try and run this again. There we go. So for some reason, sometimes Ampy might have an issue connecting to board, so just try again after that. And so it's a little bit slower. Let's, uh-oh, here comes the cat. We might have a visitor here. She's walking by. She's a big fan of the OLED display, so might not be able to see. Let me zoom out here. Oops, there we go. This is have a little visitor. I think she's a fan of the OLED displays. So okay, well, I think you get the gist of it. I'm gonna wrap up this stream. I don't want to drag on for too much longer, but I wanted to show that this is a real example of something fun you can do with this OLED. There we go. The cat's gone, so we'll zoom back in on this message here. So that's that's a real fun example, and I might turn this into a wearable where I'm going to take, we have a short version of the headers, so you can see these headers are pretty thick, and this thing's pretty tall, but there's a version of these headers that are about half as high, and so it makes it nice and slim and small. And so I might do this and make it like a little wearable name badge that I can set ahead of time, and we'll just scroll little messages across with MicroPython, because I like the idea of fun little MicroPython wearables and things. So be on the lookout for that. Actually, I'll be down at the Super Conference, for the Hackaday Super Conference in LA in a couple weeks or so. So if you're down there, you might see me wearing this or some other MicroPython wearables. So okay, if folks have questions, throw them into the chat. And again, apologies for the audio. I'm not sure why it's only in one signal. I changed my microphone amplifier setup, and I realized that my Mac, I think it's only a mono speaker, and so that I've never even noticed that it's not stereo. So I'll try to fix that for the next stream. Hopefully it's fine for folks that are watching it right now. But again, if the audio is completely unintelligible and horrible, check out the guide that I mentioned, this SSD1306 guide. This has all the details I just went through in this video, so you can see kind of what I went through and how to load this and start using it yourself. So okay, we'll jump back to the main view. So let me go here. We'll turn that off and that off. So okay, cool. So that was the stream, and I don't see too many questions. So yeah, so I'll wrap it up. So thanks a lot for watching. It's Tony from Adafruit. Check out youtube.com/Adafruit. You can see this video, all kinds of other fun project videos there. Check out twitch.tv/Adafruit. That's where I like to live stream things. I do a couple live streams a week, sometimes on a Monday and a Friday. I at least like to do a Friday live stream, but the Monday one I might move to like Tuesdays, just because sometimes it's a little bit hard to get everything all together for that. But definitely keep your eyes peeled. There's going to be a lot more guides on MicroPython hardware, and specifically all the feather wings that we have. So like I mentioned, there's the servo and the PWM feather wing. So keep your eyes peeled. I'm going to be cranking out hopefully some more guides and videos on how to start using a lot of the other feather wings, because then things will start to get really cool, where we've got like a motor feather wing, relay feather wings, things that you can start controlling things, building robots, maybe some IoT projects in the future. So I think we're going to start getting into some really cool, fun MicroPython stuff now that the basic kind of building blocks are here for using modules and using little boards like the SAMD21 board. So if you like MicroPython, I think you're going to like what we've got in store for you soon. So okay, that's it. I'll wrap up the stream then. Thanks a lot for watching. Like, comment, subscribe. Let us know that you like this content and that you're learning good things from this, and we'll keep doing it. So thanks a lot. It's Tony from Adafruit. I'll see you guys later.